Okay, so today we're going to be doing an activity on surface area and nets. They're basically the exact same thing. When you think of a net, it's something that you throw over an object and it takes the form of whatever object it happens to be covering and doesn't care about the volume, but just the outside area of that object. And surface area is going to be the same thing. It's going to be talking about how much area and what is actually just on the outside of a shape. So here we have our rectangular prism. It's our blueberry jello flavor for the night. And we have our rectangle base. We have our faces and our other base on the bottom. So we are going to lay it down and take our shape and we're just going to trace around it, kind of line it up a little bit on the corner to get our initial base shape. Okay, so we have that. Then what you can basically do with a net and your object is we're going to tilt it because we want every side to be able to be wrapped with our wrapping paper. So we have it here. We are going to go over and again along the outside of it, make sure to line it up. Okay, so now we have that face has been incorporated into our surface area. I like to tilt mine up this way. There's a couple different ways that obviously you can do it. So again, I'm going to extend this out. So I have that face. We're doing our side over here now. Make sure it's relatively lined up. All right, and we're going to do this face as well, but then we're going to make sure that we include the top base. So you're going to actually flatten it down and say, okay, make sure I'm kind of lined up, using that as somewhat of a guide on my side. And I should have 1, 2, 3, 4, 5, 6 faces. Technically, 4 faces and 2 bases give me 6 surface areas. I'm going to clean up this side a little bit over here. So this is what is called a net. When we get through cutting this out and folding it up, it's going to cover our shape just like that. Now, sometimes what you can also do is include, in our situation, sometimes a little bit of a flap. This little area that kind of sticks out. And this will allow it, when you cut the shape out, that it kind of gives you something to kind of grip onto. So those are going to be connected. So again, kind of add little extra flaps here. All right. So I'm going to pause the video. Feel free to cut out your shape. I'm going to put a flap here. And I'm going to put another flap here. All right. So again, what you see that's in our red is our shape, and you'll see it better obviously when I cut it out. Out my net. This is the area that would go around my shape and cover every single side, aka the surface area. And so when it comes to the surface area, we're finding the area of the surface. So we're going to look at each shape, and that's really important. Whenever you do any nets or surface area, you have to consider all sides of the figure and find the area of each one. Top, bottom, front, back, left, right. So we're going to say over here, we have basically, it's about 1.5 by 4. So this one we're going to say has a 6-inch squared surface for this area flap here. And since this is a rectangular prism, and over here is also going to be 6-inch squared. Okay. My inside, I kind of rounded it of a 4 by 3.5. So that got me to 14 inches. And my top and my bottom are going to be the same. So this is also going to be 14 inches squared. So you should be calculating that up. And we are going to basically say here, this is 1.5 times 3. 1.5 times 3 gives me my 4.5 inches squared. And over here, same thing, 5 inches squared. So most oftentimes, especially with rectangular prisms or anything like that, your front and back should be the same, your sides should be the same, and your top and bottom should be the same. So to find our total surface area, the only thing we now are going to do is add up the individual areas. So 4.5 plus 4.5 plus 14 plus 14 plus 6 plus 6. And obviously you could do 6 times 2, etc., etc. So my surface area, and since I added them and not squared them, my exponent is still going to be the same, is going to be 49 inches squared. That is my surface area of my rectangular prism. So once you have that, and that would apply to all of them, you can actually now take, and I had my little flaps and I had folded them back just to make the figure look a little bit more like it's supposed to with the nets. And you can either use a glue stick if you happen to have a glue stick, you can use tape, whatnot, and we are going to fold this up and make our rectangular prism. All right, so see that in just a moment. So we have our shape here, and this is what I got when I took the circle of my cylinder that I have, and then I would label it and roll it down. Again, here's my marking. I marked to make it, and a little bit more, so you're welcome to add a little bit more, and that's fine, just for our example. And tip it over, and again you do the outer edge here to create our top circle. And we are going to note the fact that this shape here is a rectangle, and the rectangle has the same width as is the circumference of our circle. So, and the height of the label is equal to the height of our cylinder. So that is one thing and that you can note. And when it comes to wrapping and finding the surface area of any cylinder, it's a matter of having two circles and a rectangle whose width is equivalent to the circumference of the circle. So we're going to put a few tabs and cut this out and start finding its surface area. Right. So I've cut it out. I have my little tabs to help me when it comes to assembling it. And I have my dot in the middle and my radius, which is the distance to go from the center of the circle to its edge. We need to remember that to find the area of a circle, it's pi r squared. Pi basically being 3.14, radius, distance from center to the edge, squared means you're going to times it by itself. So this was basically 1.25 inches. Each one of these little squares is a square inch, 1 by 1, which came out to equal 4.9. So for this activity, I'm just going to round that up to 5 inches squared. And so just like with the rectangular prism, a neat thing about this is that if this is 5 inches squared, then automatically this is also 5 inches squared. So then it comes to finding the area of our rectangle. Now, the formula for circumference is c to pi. Okay? C to pi, and remember diameter is equal to twice the value of our radius. So 1.25 in my situation times 2 times pi was 7.85. So this length here is 7.85 inches, and that's just for my length. Times 2 gives me 15.7, which I'm going to round up to 16 inches squared. So I have 5 plus 5 gives me 10 plus my 16. So that means my total surface area for my little can of black olives is going to be 26 inches squared. That is my surface area. That is the minimum amount of squared inches of wrapping paper needed in order to cover the entire surface of each one of these areas. So figure that on your own shape, and let's go ahead and assemble our little cylinder and see what it looks like. So go ahead, figure out your surface area on yours, and go ahead and put it together. Okay, so if you're struggling a little bit with some of these, that is perfectly fine. That happens, especially since the circumference is sometimes a little bit harder to do and get exactly right. So if yours ends up a little short, a little off, that is perfectly okay. As you can see, it's a little bit rough, but the concept is there. We have a perfectly hollow three-dimensional cylinder that has nothing but pure surface area for our little gift here, right? So there we go, and we are going to put that aside, and that had our total of 26 square inches is the surface area of our little cylinder. Right? So let's put that aside and see what we have next. So next I'm just going to use some brown paper here for this activity. And what we are actually going to do is build a little Christmas scene. So if you happen to have some brown paper or anything like that you can color brown, feel free to do so. So I'm going to make a triangular pyramid for this situation. We can do it as a prism as well. So you can have a choice which one you want to do. So you can do a triangular pyramid or a triangular prism. And actually, let's go ahead and do the prism, and we'll save our pyramid for later. So with this, I'm going to draw a 2-inch line segment. I want to make sure I have at least 3 inches from the side, so excellent. And I'm going to draw a 2-inch line segment. I am going to find my bisector. Okay. And I'm going to create my perpendicular bisector. Okay, so what I've done is I've taken my ruler and I'm basically using it to create a perpendicular line here. And so since this is flat along the edge, if I put it all the way along here, I have a 90 degrees that I'm formed. And I put it flush to my line there. And I'm going to do basically 6 inches from here to here, because we want to be able to make 3 2-inch markings. So towards the middle, because you want to have room over on this side and this side of it. And so we are going to, for me, I'm going to start at 1 and go all the way up to 7, because that will give me a 6-inch span. And then every 2 inches, I'm going to make a line and our markings. Okay, so this is 2 inches across, which makes it nice. I can then just slide over and again kind of line up my bottom to make sure it's flush. And again, I'm going to go from 1 inch up to 7, making marks every 2 inches, and going to connect them. So this is 2 inches by 2 inches. Along this side here, go ahead and find the middle, the midpoint. And we are going to create the perpendicular bisector on this one going out this way, because we're going to create our triangle over here. We're going to make this into a triangular prism. So one way, I'm just using my line of my 9 and make that flush. And if that is flush, then it should come out for your 90 degrees. And I'm just going to draw that up. Now, a thing about the perpendicular bisector is, you remember, any point along the perpendicular bisector is equal distance to the endpoints of that line. So we are actually going to do 2 inches up. So on your ruler, find one here. I'm going to put it at my 9, which means my 2-inch mark will be at 11. And connect my point. Okay, I'm going to do the same thing over here. So you're going to do 2 inches over here as well. 11, and for me a 9. And we have our 2 inches. So our height at that point, which is going to be important, can measure it. And the height is basically 1 3/4, or 1.75. So we are going to do the same thing that we did on this triangle over here. Okay, so close this up. We are going to find the midpoint. Midpoint is the point in the middle. We're going to construct a perpendicular bisector. And perpendicular is 90 degrees. Bisector means in the middle, or cuts in half. Okay. Any point along the perpendicular bisector is equidistant from the endpoints. So we're going to do, if we wanted to, we could probably even measure up 1 3/4 on the point and double check our 2-inch mark. But I'm just going to do 2 inches from perpendicular bisector to endpoint. And again, and there we go. So we have now the net of our triangular prism. So what's kind of neat to see is the fact that it is made up of either rectangles, or in this case squares, because what I have is an equal angular triangle or an equilateral triangle. All 3 sides are congruent, and also all 3 angles are congruent. A 60, 60, 60. So since all 3 sides are congruent, that means this is 2 by 2 or squares. If you had any other length on your triangle and it was an isosceles triangle, then these would be rectangular. So we're going to put some flaps on here, and let's cut it out and start assembling. The area of a triangular prism. So we have to apply our 2-dimensional rule of a triangle, which is base times height divided by 2. And we actually got a unique situation here, because 1.75 times 2 divided by 2, our 2 divided by 2 are actually going to simplify out and my answer is going to be 1.75. And the fun part about that, because if you notice this distance here, if I just did this and folded it over to create a rectangle, it'd be a 1 by 1.75 rectangle, which base times height would give me 1.75 inches squared. So this area and this area are congruent. So this is 1.75 inches squared. And this is also going to be 1.75 inches squared. So together, we add them up, so we times them by 2 to get our quantity, which is 3.5 for our two triangles. And then we have to find the area of what traditionally is usually our rectangles. In this situation would be our squares. So 2 times 2 just gives me 4 inches squared. And then 4, 8, 12, or 4 times 3, because there's 3 faces on this. And so 12 plus 3.5, these two added together, gives me a total surface area of 15.50 inches squared. So when it comes to finding the surface area of a triangular prism, base times height, and basically you can leave it like that, because divided by 2, but then you have 2 of them, is basically the same thing as an equivalent of base times height. And then you have 1, 2, 3 of your rectangles. So go ahead, pause the video, and let's go ahead and assemble this. Tape or glue stick, and make it into our prism. Okay, so hopefully you folded up your triangular prism. A little bit of glue, a bit of tape helps secure it, and you'll see that you have your 2 bases. You'll have your faces and your total surface area of 15.50 inches squared. All right, so we have that, put it with our others, and let's see what's next. So up next, we are going to make a hexagon pyramid. So in order to do that, I have my green sheet here that we're going to use, and we're going to cut it basically in half is what we're looking for. So if it's an 8.5 by 11, 5.5 is going to be basically there. And if I line that up, let's find our, so if it's 8.5, so I need 4.25, which is going to be that mark there. Remember the longest one in the middle between them. So we can go ahead and zoom in just as a quick refresher. A little hard to see with the lighting, but the longest one in the middle, that's our half. Then we have a quarter, okay, and etc., eighths and sixteenths. So 4.25 is going to be right there. So let's get this back over to my 5.5, and I got 4.25. And if that's basically flush, we can do and make sure we get another 5.5 mark over here. If you have at least 2 dots, 2 points of which a line can go through. So we are on par. close enough, and go ahead and draw our line through it. 4.5. Let's get another 4.5 dots so that way we have 2 points. Through any 2 points, there is only one line that can draw through them and connect them. So I got my second point at 4.5. So right now I am just connecting them in order to continue to cut my paper into force. Right, so center of the paper, and we're going to do 1.5 inches in either direction. So let's do 1.5 inches, so I'm going to do 5.5 one direction, and 1.5 inches would be 3.5 in the other direction. And this is going to be the outside of our hexagon. So we're going to follow the same rule that we did last time in terms of the perpendicular bisector rule. So let's bisect this half here. And you're going to see what I'm going to be doing in just a moment. So half of 1.5 is actually 0.75. So I'm going to do 1/4, half, 3/4. Okay, 1/4, half, 3/4. So this is our midpoint. This is our edges, and that's our midpoint. So what we are going to do is line this up. Sometimes what I like to do is just again use kind of like this big line here and put it up against that dot and kind of line it so it is an extension of this line here. That's kind of a one cheat to be able to make some relatively perpendicular lines. And we're going to extend this in either direction. Okay, same thing over here on this side. Again, and we're going to extend it in either direction. So I'm creating the perpendicular bisector between this line segment and this line segment. So what I can do, since this here was 1.5 inches, and we're going to have each of our line segments be 1.5 inches, I can now take this end here and pivot, 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 pivot until I get to 1.5 inches, and then can connect those points on that line segment. So traditionally I would connect this back down here, and what that would do would create a 60-degree angle. And since this is a hexagon and there's 360 degrees in a hexagon, each side is basically going to make a little 60-degree, 60-degree, and 60-degree triangles. So we're following the same rule that we just got through doing with equilateral triangles, and now basically sticking them all together to create a hexagon. So I've about 1.5 inches. Get my satisfied there. So that's 1.5 inches. So what you'll find is when we go to connect these 2 points, what do you notice? They're 1.5 inches. And that's what we want for a regular hexagon, is for all the line segments to be congruent. So since this is still the perpendicular bisector down here, I'm just going to do the same thing down here of going 1.5 inches between my perpendicular bisector and my endpoint. Over here, the same thing, 1.5 inches. Connect them, 1.5 inches, beautiful. And I have my perpendicular bisector. So this is 1.5 inches, this is 1.5 inches, etc., etc., etc. And I have my hexagon. Alright, so now that we have our hexagon, what we're actually going to do is create, for the pyramid, we have to create the triangles that extend out on it. So the nice news is we actually have one partially started for us. And we're going to follow this concept around again to find our perpendicular bisectors. So we're doing perpendicular bisectors all over the place. 1, 2, 3 gives me my 3/4. 1, 2, 3 gives me my 3/4, my midsection, or my midpoint, and midpoint. Okay, create the perpendicular bisectors. Now if you notice, you have a point over here and now a point over here. Through any 2 points, there exists only one line. That is a geometric truth. So you have your 2 points, boom, boom, extend them out, and we now have our perpendicular bisector for each of these sides of our hexagon. And what that means is that I connect the point, I can plot a point anywhere along them, and they'll be perfectly congruent to the either sides. So you want to pick your short side of your paper, and I can do about 2.5 inches, it looks like. Double check over here to make sure. Yep, I can do about 2.5 inches over this way as well. So any point along the perpendicular bisector is congruent to the midpoint, so 2.5 inches. I plot my point there. I can automatically just connect it. And boom, it is congruent. So same thing here, I'm going to do 2.5 inches. You want to make sure that they're all the same distance. So that way when they fold up, this one was almost exactly 2.5. Okay, measure twice, draw once. And last, oh no, not quite last. Alright, so keep this up, go on all the way around. Half, 2.5 goes in either direction. There we go. Now last but not least, 2.5 and 2.5. Okay, so we now have, actually it looks like a pretty cool star, and that's what the foundations and the net is for a hexagon, or basically any main polygon pyramid that you're going to have, is that you're going to have the foundational base, whether it's a hexagon or an octagon or any other dodecagon, whatever you want, and then from it is going to be numerous amount of stars, or excuse me, triangles. It looks like a star. Triangles. And obviously the base of the triangles are going to be congruent to each side length of whatever your polygon is. And so then you just need to find this lateral height or height of the triangle, find the area of one triangle, and multiply it by the number of sides on your polygon. And the polygon, as you know, has its own formula to find its area, which you find by using the apothem, which is basically nothing more, again, than its own little triangle. So apothem times side length, right, divided by 2 times number of sides. So we're going to have basically little triangles on the inside to create our polygon, and little and bigger triangles on the outside to create the actual pyramid itself, and that number times the number of sides of the shape. So I'm going to create some flaps on this so that when we fold it together and cut it out, that they all kind of stick together. So I'm going to do that and cut this out. You pause the video and do the same. I've put the flaps, I just folded them on the back so it's easier to actually see the real shape itself. So let's again talk about how to find the area of this situation, a hexagon pyramid. So we can have two parts. We have the parts of the inside of the actual hexagon itself, and then we basically have the triangles on the outside that create the pyramid component. To find the area of the hexagon, we take the apothem, which is the distance from the center of the circle to 90 degrees on a side, which in this case is 1.25 inches approximately. And that basically becomes the height of this little miniature triangle that's inside of it. So height times base, which is 1.5, divided by 2. And so we're going to take that, and then we're going to times it by 6, because there's 6 of those little triangles inside the shape. When we do that, we basically get that each triangle is going to be 0.9375, which is basically 15/16 inches squared. So when we multiply that by 1, 2, 3, 4, 5, 6 triangles, because this is how much is in one triangle, and we have 6 of them, that gives us a grand total of 5.625 inches squared for our base here. So that is our hexagon. So now let's look at our exterior triangles. These up here. So we're going to do the same basic thing. Base times height divided by 2 times 6. So 2.5 times 1.5 divided by 2 gives me 1.875 inches squared. And that's how much is in one of these triangles. And the nice thing is they're all congruent. They're all the same. So this quantity times 6 gives me 11.25 inches squared. So this here is my hexagon. This is all my exterior triangles. So in order to find my total surface area, I'm going to add these two together. So my surface area for this hexagon pyramid is 16.875 0.5 inches squared. So I know it's a lot of little numbers, but you want to just also pay attention to the initial concept and what it takes and what it looks like to create this shape. So what we can do now is actually fold it up, and I'm going to fold my flaps back out, and let's assemble my hexagon pyramid. Pause the video and let's see what it looks like. I'm going to throw on some little spots, little decorations onto it, and you have your now hexagon pyramid because it comes to a singular point with triangles. And then if by chance you happen to have a little pipe cleaner star, and you can put all of your three-dimensional surface areas together, and well, I hope you have a Merry Christmas, and I hope this helps.